Okay, moving on. Let's look at inverse functions. So here in problem 4, it wants us to determine what makes a function one-to-one. Well, a function, if you remember, is a relationship between domain and range in which each member in domain corresponds exactly one member in the range. Well, in a one-to-one function, we go the other way. Each output, right down here, each output in the range corresponds to exactly one input in the domain. Right? So with that said, right, inputs and the outputs do not repeat. So you shouldn't see any repeated inputs. We talked about that with functions. And the same thing now goes for the outputs. All right. And we also talk about functions graphically, right? We talked about the vertical line test to prove each input gives you exactly one output to make a function, right? A vertical line can only cross at most one point. Well, in a one-to-one function, not only is it a function, does it pass the vertical line test, it also passes the horizontal line test. So it passes both the horizontal line and vertical line tests. Let's put it on there. All right, and remember, what I mean by passes it, all right, cannot intersect at more than one point. All right, another thing graphically, characteristic, a one-to-one function is always increasing, all right, or decreasing, one or the other. So there's no change in behavior. Right? You're not going to see any turning points. You're not going to see a change from increasing, decreasing, or decreasing, increasing. All right. And now moving on to number 5, it says, how do you know if a function will have an inverse function? All right. It's got to be one-to-one. That's what the whole purpose behind one-to-one is. You say, well, why does it matter if it's one-to-one? Well, if it's one-to-one, its inverse will be a function. All right, so now let's talk about inverse relationship. So we're talking about inverses. Well, down here you see the graph of a function. All right, each x gives you exactly one y on this graph. Right, you can see it passed the vertical line test. It would also pass the horizontal line test. Right, so you could turn that around and say each y will give you one x. So yeah, each input gives you exactly one output. Each output will give you one input. Now let's talk about some of these inputs and outputs by looking at a few of these points. So I'm going to mark a few of these. So we've got a ordered pair on this graph of this function. This graph begins over here at -5, -3. So we'll plot that point. We can see our graph of this function passing through the point -2, 3. Right, and we see our graph passing through the point 3, 6. And we see it passing through the point 8, 7. All right. So just looking at a few points here. Now this is the graph again of f of x. Now I want to look at its inverse function, which is notated f superscript -1. So we're talking about the inverse, right, function. So that's our notation there for inverse function. Got a superscript of -1. That's not an exponent, doesn't have exponent properties. Just signifies we're swapping out the relating variables. So we're talking about finding the inverse function. We're going to interchange x and y, right, to do the inverse. So with x going to y, now we're going to look at y and x. So with -5, -3, let's interchange, right, those two values. So to find the inverse function, right, we need to interchange x and y. Swap them out. So -5, -3. Well, as we look at the inverse relation, -3, -5. So left 3, down 5. I'm going to plot that point. So here, -3, -5. So there's the inverse relationship. So again, you can see x and y. I'll make that note here. X, y. And then in the inverse relationship, we have y and x. All right. Now let's go ahead and do the same thing with the remaining points. -2, 3. So as we look at the inverse relation, it's going to be 3, -2. So right 3, down 2. I'll put, again, this new graph in blue. Interchanging x and y, looking at the inverse. 3, 6, well, we know we're going to have 6, 3. So there's our ordered pair, 6, 3. 8, 7, we're going to have 7, 8. So right 7 and up 8. So we plot in that point. Now let's connect these. So looking at our graph, right, as we look at the graph of this inverse function. Right. There it is. So there's its inverse relationship. All right. So looking at inverses, we're just interchanging the relating variables, right? X and y, y and x. We know it must be 1 to 1 for its inverse to be a graph of a function. So you can see your function graph, of course, passes the vertical line test. Right, each x, each input gives exactly 1 y, 1 output. All right. Now moving on, speaking of inverses, let's go to problem 7. It says use composition to show that the following functions are inverses. Well, function graphs, when you look at their inverses, right, their symmetry line is the line y equal x. Right? Two graphs are symmetric to the line y equal x if you have inverses. And the same thing goes with composition. So when we compose inverse functions, so if this is an inverse function, we know that f composed with g of x should equal x. All right? So again, if they're inverses, y must equal x. All right, so let's go ahead and see if that's true. So f composed with g, so we know how to do composition. That's, of course, defined as f of g of x. So we're going to go ahead and evaluate this function with an input of g of x. So it would be f of -3x plus 12 as we substitute g of x in. And then we go evaluate. We go to the f function. Wherever we see the x term, we're going to plug in -3x plus 12. So let's go ahead and do that. We see our first term in the f of x function is -x over 3. So I'm going to go ahead and input g of x, which is negative 3x plus 12. Put it here in a different color. All right, so again, replacing the numerator of the first term there in the f function. So x over 3 is now g of x, right, over 3. We're trying to evaluate f with the input of g, doing composition, and then we got our plus 4. So again, wherever you see your input variable, we're plugging g into it. Now, as we simplify, all right, my goal is, remember, to get down to x. So what I'm going to do is go ahead and take this fraction, and let's go ahead and, if you want, we can separate these two terms. We got a negative, right, of negative 3x, right? So again, you can go ahead and break that up into two fractions, negative 3x over 3. All right, and then we've got our negative to distribute to the next term, which is a 12 over 3. So applying the distributive property, right, distributing the negative through, right, both of those terms. And maybe, just sometimes people have trouble seeing that. Let's go back. We'll go ahead and do the distributive property first. Go ahead and take care of this negative. So we'll go ahead and distribute here to simplify. So we got negative 3x, which is 3x, and negative 12 is 12. So 3x over 12 minus 3 plus 4. And then as we break that up, that's equal to 3x divided by 3 plus 12 divided by 3 plus the 4. And what is 3x divided by 3? That's x. That's a minus 12. Let's check my notation there. As we distribute, that became a minus. And minus 12 over 3 is minus 4 plus 4. And we know that minus 4 plus 4, that's 0. So we get x back. So that implies f of x and g of x are inverses. Right? So that's our test line, y equals x. Right? And if you were to graph the two functions, they're going to be symmetric to the line y equals x. If you were to look at the sketch of those two lines, right, if you were to graph them there, you can put them in your TI to see that. So I always like to show that, right, with inverses. So maybe while we're at it, let's go to our TI calculator real quick. And let's put these two functions in there. I'll show what I mean by that. So I'm going to bring up my calculator. I'm going to go to y equal, and I'm going to store in negative x divided by 3 plus 4. I'm going to put that here in y1. And I'm going to graph g of x and y2, which was negative 3x plus 12. So those are the two functions that we were given to see if they were inverses. And if we graph these, and I'll graph them on a standard window, Zoom 6, you see the graphs of these. And if you go down to y equal, let's go to y3, and let's put in the line y equal x, right? And when you graph in that line, you see the, right, symmetry with that. So you can see your symmetry take place, right? Where do they intersect each other? Right, they're equal at x. Right, that's the intersection of those graphs. So again, it creates that symmetry. Right, so looking at inverses. Now let's find a inverse function, all right, by hand. So let's take this function f of x equal to the square root of 4x minus 10, or I should say square root of 4x minus x plus 10. Is it 1-to-1? Find its inverse function. All right, so we'll do that in a second. Maybe we'll take a little break. We'll come back to that one. Let's stop there for now.